question 3.1. In figure 2, here, the cell has an EMF, electron in motion with due to a force or electromotive force, and internal resistance R. The EMF supplies energy to the valence electrons in the wire, and this valence electron will then flow in that direction from the negative end of the battery. So that's a negative, this is a positive. And so the electron flows here, and the current will then flow in the opposite direction. We've got the load resistance, and the terminal PD. The current in the circuit is I, and the potential difference across the load R1 is V1, and the potential difference across the load R2 is V2. So those are the terminal PD. We need to explain how the law of conservation of energy applies in this circuit. You should consider the movement of 1 coulomb of charge, a charge is the electron, around the circuit. Well, in this case, the conservation of energy is referring to the Kirchhoff's second law, which is the conservation of energy, because whenever we're talking about energy, we're referring to the potential difference here in a circuit. Potential difference supplies the energy to the electrons. Therefore, the total potential difference here must be equal to the sum of the total potential difference of the terminal PD. And that's Kirchhoff's second law. But we need 2 points here, so you can write down any of these values here. So E, the energy, can be considered in terms of the electron volt, which is the voltage supply to the electron. So that means the voltage is supplying the energy to the electron here. 1 coulomb of the charge gains 1 joule on passing through a cell. Or you could say the energy transferred by 1 coulomb in R1, the load resistance R1, is the voltage across R1, which is V1 in joules. Another way to say it would be the energy transferred by 1 coulomb in R2 is V2 for its voltage. Another way to say this would be the energy transferred by 1 coulomb in R. This is the internal resistance of the EMF. So this one too will have its own internal resistance, and that's little r, is the current times resistance for the joules, because that will be the voltage across the internal resistance. Or you can now say for conservation of energy, which is the Kirchhoff's second law, which states that the total energy from the power supply, from the voltage, the EMF, is equal to sum of the voltage across the load, voltage across the internal resistance. So this will be V1, this is V2, and this is a V little r. And so sum of the voltage must be equal to the sum of the EMF. And that's the energy supply. That's Kirchhoff's second law, which is the sum of the EMF, that one, is equal to sum of the potential difference across the system. Figure 3 shows a variable resistor, this one here, made with a thin conducting layer on an insulating base. The conducting layer has constant width and thickness and has connection at the ends A and B. C is a sliding contact, so that makes it variable. Sliding contact that can move along the surface of the conducting layer between A and B. Figure 4 shows a circuit that uses the variable resistor as a potential divider. So that means there's a potential here which is equal to the potential there, but this bit here is dividing that potential here into 2 parts, one for here and the other will be that one, and the sum of the 2 potential will be equal to that. So the potential here, the EMF is 3 volts, and it does have internal resistance R. The variable resistor is connected to a battery of EMF 3 volts and the internal resistance R. The resistance of the conducting layer between A and B is 125 ohms. So between there and there is 125 ohms, and then this one has its own resistance as well. So the total resistance in this system will be 125 ohms plus R. Question 3.2. The sliding contact C is moved to end B of the variable resistor. The switch is closed and the digital voltmeter reads 2.89 volts. So show that R is approximately 4.8 ohms. So we're saying that C point has gone to the end here. So that'll be 0.2125 because that whole resistance is 125. So we're trying to find the internal resistance in this case. So the first thing we'll do is to use remember Ohm's law, V equals IR. The EMF, which is from the cell, we know using Kirchhoff's law, second law, or the conservation of energy, will be equal to V1 plus V2 plus IR, or V little r. So we can say that the EMF is the V little r, which is current times little r from Ohm's law, plus the total voltage 2.89. Now we can say V2 is IR2, because current flowing through this, current flows in that direction. This is positive, that's negative, positive, negative. The current will flow there in that direction. So the current flowing is in series, so the current is not splitting. So there's no Kirchhoff first law. Fairly say that this is the same current that goes through V2 and V1 and R. So the current can be V2 over R2. We know the voltage of V2 is 2.89 divided by 125. So what we're saying is the voltage, this is now the V2, because that V2 is here, so it's covering the whole thing. We're finding that current, and that current is, because the total resistance is 125, so the current will be 0.02312 amps. And then now we know the current, we can write down the Kirchhoff's second law, the conservation of energy, which says that the EMF is equal to IR plus 2.89. This is the V, the load voltage. And we can find IR to be the difference between these two by just rearranging to make IR the subject. Now we want to make R the subject. So R will be that, the EMF minus 2.89 voltage divided by the current. And we plug in the values, 3 minus 2.89 divided by 0.02312, and that gives 4.76 ohms. So very close to the expected value for R, which is 4.8 ohms. And so we're quite happy with that. Question 3.3. C is set at 1/5 of the distance between A and B, so 1/5. The thickness of the conducting layer is uniform, so the resistance between A and C is 25 ohms. Determine the voltage reading at this setting. So we got C there, and we need to calculate the voltage. So this is a potential divider, because we've divided this AB into 2, and the total resistance in this case will be the load resistance plus R. And we know the load resistance is 125 plus 4.76. We calculated that earlier here. And the total resistance will be 129.76 ohms. So we can talk about the resistance that will split, and that will be the ratio here. We've got the uniform of resistance between A and C is 25 ohms. So 25 to 129, 7.6. V, in terms of the voltage, is going to be V to 3. We know the voltage of this one, which is 3 volts. We need to find that voltage, because that's what we're told to find. So if I do that divided by that, which is that over that, equal to that divided by that, and I can work out my V by multiplying both sides by 3, and that voltage would be 0.58 volts. So the voltage reading that we're expecting should be 0.58 volts. Could have done the same thing by looking at the terminal voltage, which was 2.89 volts, and it then says is 1/5 of that. So you could have done 2.89 divided by 5. You get the same thing, but that's quicker. Question 3.4. Figure 5 shows a variable resistor similar to the one shown in figure 3, but with the following 3 manufacturing faults. At P, this is P here, the conducting layer changes in thickness so that AP is thinner than BP. At Q, there is a scratch into the surface of the conducting layer and across its full width. So that's that one there. From R to B, the conducting connector is laid over the conducting layer. The width of the conducting layer is constant, that one there. The black one is the conducting layer. A potential difference of 3 volts is applied across A and B. And so that will be 0 volt, 3 volts. The difference between the two is 3 minus 0, and that's 3 volts. C is moved from A to B. Sketch on the axis in figure 6, this one here, a graph to show how the potential difference between A and C varies as C is moved from A to B. Divider, and so you move now across So you're going to get different potential because of different thickness. Applying the V equals I out, and the resistance will vary here because of the thickness of the material. So there's a constant resistance here up to that point there when you're plotting Udemy over the distance there, and a different resistance here, increasing resistance, decreasing resistance, increasing resistance, and conducting layer. So we expect to start with that point there, and we want to go all the way along there where it's going to be uniform voltage. So uniform voltage or steady voltage due to the distance. And so we can draw that line there. And when we get to that point, the voltage will be, the gradient will be less because of the increase in resistance, because the current will be less. So we'll expect the gradient to be less up to that point. And when we get to here, we expect a sharp increase in current and voltage because of a completely small thickness, and it's very small. So we expect that. And we want to go from there to R with similar gradient to PQ. And so we go like that. So this and that should have similar gradient. And we got to this point here. There's no resistance because this is a pure conductor. So we expect to be horizontal line there. So that's the kind of diagram we should get.